Hello, compadres. So, we come back to a idea that we began the other day, and that is that if there were but one object in the universe, what would it do? Well, what we said is that this mass creates a gravitational field. All right? And so we said that if we look at different locations in space, at different distances away from the center of this object, there are different gravitational field strengths. All right? The strength of the field made by this mass depends on a couple of things. It depends on the mass of the object, and it also depends on how far away from the object the place in space we pick is. Now, let's pick this place right here in space. All right, we can draw the field, because the field is a vector, we can draw it like that. Now, what does this field do? Well, what the field does, well, by itself is nothing. But if we were to, hypothetically, put a certain mass here, right? Let's put a mass somewhere at this distance away from that other mass. So let's put this mass here. We'll call this a mass M. Well, that mass M could experience a force, a gravitational force, Fg. Right? And then, of course, this would experience a force Fg, of the same size, not that big, of the same size in an opposite direction like that, right? But what also happens is, or what also could happen is, let's say we put a mass 2m here. Well, that object would experience a force 2f. Twice as long? So, what you have to notice are a couple of things. First, these force vectors in blue are forces exerted on objects, on this green mass and on this red mass. Okay? But this red vector here is the gravitational field that is not a force, right? Because this, well, is not a thing. That's a location in space. At every location in space, there exists some gravitational field. If a mass were to be placed there, that mass would experience a force. All right? But here's the thing about the field. Notice, there's the same exact field strength everywhere on this dotted line. We said the strength of the field depends on how far away you are from the center of this mass. All right? But notice, we have this much mass experiences that much force. Twice as much mass experiences twice as much force. But there's something that's the same about that. And what's the same is this, such that there is a constant value of force per unit mass, right? Case 1 is for this one, right? Well, force per unit mass is Fg over m, right? For this one, force 2F per unit, well, per mass. Well, yeah, look, same thing. So I should put the G here, gravitational force per unit mass. So that, by definition, is what gravitational field is. So it's of magnitude Fg over m. Now, but notice this doesn't say anything about how far away we are from the mass like we've been talking about, but it does. I'll show you that. But first I want to talk about that, well, this you've seen before. You've seen an equation that involves Fg and m, where in particular if you divided Fg by m, you'd get something else. And that equation is this. Subscript here, right? Gravitational force is mg. So that means that F divided by m, well, that's g. Wait a minute. I thought g here was gravitational acceleration. Well, notice what else it is. If you look at the units of this, force is measured in newtons. Mass is measured in kilograms. So we're talking about this quantity g that's a measure of the amount of force that would be applied per unit mass of the object put at that place. All right, now, we've always talked about g as acceleration and said, well, wait, isn't g just measured in meters per second squared? Well, remember what a newton is. A newton is a kilogram meter per second squared. So a newton per kilogram, oh yeah, is the same thing as a meter per second squared. So this is a pretty big deal in our race. That's not you don't really need to concern yourself too much with that, but it's not rocket science. What we're saying here is that G is two things. One, it's really gravitational field strength. And therefore, gravitational acceleration. Because we've been talking about, why do objects here near the surface of the Earth accelerate at 9.8 meters per second squared? Well, because for every kilogram of mass that you place there, 9.8 newtons of force is applied to it. I don't know if this is sort of like blowing your mind a little bit, but I remember it being kind of a big deal to me. Now, the other thing that we can say is, so this is one thing. I mean, duh, we know that, but we got to make sure that we're now thinking of it in these terms, that this is actually gravitational field strength. All right? The other thing is this, that if we say Fg over m, now, m, which m? This one or this one? Well, it's this one, right? That's the mass we put in here. So let's say we call this, I don't know, Earth and satellite. Okay? If we talk about the gravitational force between Earth and satellite, it's not a G, that's an S for satellite. Well, gravitational force is G, mass of the Earth, mass of the satellite, over square of the distance between the two. But look, divide by mass of the satellite. Put a mass of the satellite down here, and look what goes away. And here's another expression. Well, that's what G is. Or that's how you express G, gravitational field strength, in terms of the mass that made it. Now, what I'm going to do is get rid of this. I used the E before for Earth to just illustrate the fact that when we write that second equation that we just wrote, we use the mass of the thing that made the field, as opposed to here, where we use the mass of an object in the field. And that's a really, really tricky thing to keep straight. All right, but here are two expressions, well, really for two things: gravitational field strength and therefore gravitational acceleration. All right, and this fits what we said. How strong is a gravitational field? Well, it depends. It depends on a couple of things. One, the mass of the object that's making the field, and two, how far away from the field you are. Sorry, how far away from that mass you are. Up here, we look at this one. We say, how strong is a field? Well, it's of such a strength that a certain amount of force would be applied to whatever mass you put there. All right? So let's look at a couple of specific cases. This is planet P. Oops, planet. Come on, what are you doing? Planet P. And planet P has a radius RP. Capital R, special radius. All right, let's look at gravitational field strength in a few places. One, let's look at G here. And two, let's look at G here. All right, so here's what we would say. We would say at this location, G equals G times the mass of planet P divided by, well, R squared. And remember, this is distance from M's center. Well, so here's what we can say. Let me move this little guy. Come here, buddy. Are you there? There you are. Whoa! Don't want to do that. Move. Just delete. See it. So at this place where we are, we're actually talking about, this is G at the surface. Is G times the mass of the planet divided by, well, how far is this place from the center of the planet? It's the planet's radius away. That's square, of course. So that goes for any spherical object. If you want to know any planet, any satellite, any moon, any star, if you want to know gravitational field strength at the surface of that planet, that's how you do it. You should check for Earth. I happen to know that the Earth's mass is roughly 5.98 times 10 to the 24th kilograms. Who doesn't? And that the radius of Earth is, 6.37 or so times 10 to the 6th meters. That old song. So you should find G at the surface of the Earth. And duh, you better get 9.8, because that's what it is. So just confirm that it works. Now that works for gravitational field strength and or acceleration at the surface of any planet. But let's look at a place, there, where this is 2R planet. Well, what would happen to G here at this place in space, not a mass, right? This place in space, here we would have G is, again, G, mass of the planet over how far away from the planet's center you are. Okay? Now, notice that here's what we've done. We've said G, mass of the planet. We've made the separation, or the distance away from this planet's center, as twice the planet's radius. So what that does is make this 4 RP squared. And look, G at the surface is that. G twice as far away is that, but with a divided by 4. So one thing we could just sort of use that basic numerical relationship to say twice as far away, G here is G surface over 4. That's just, one of an infinite number of places where we could look at how the gravitational field here is different or relates to a gravitational field somewhere else. Okay? So the field gets weaker and weaker with the square of separation. Okay, but at any place, right, at any distance from the planet's center, we can just find gravitational field strength and gravitational acceleration, same thing, using that expression. Okay? So why do we say that G is just 9.8 at the surface of the Earth when it really changes with, it changes. I need a new slide, but I don't have one. Just get a new slide. So, if this is the Earth, I mean, really what happens if we draw the Earth's gravitational field, we can draw it like this as a bunch of vectors that point towards the Earth's center. I hope I said a minute ago that these are vectors and not forces, right? So we can draw these gravitational field vectors like this. They all point towards the Earth's center, all right? And you can tell this whole idea of drawing a field with field lines, we call this, we can tell how strong a field is where the field lines are closer together or farther apart. We know the field is stronger here than it is here, and we can represent that graphically with a drawing by saying, well, look, of course it's, stronger apparently means where lines are closer together. Weaker means where lines are farther apart. All right? So getting back to, but what about the G is quote-unquote constant near the surface of the Earth? Well, near the surface of the Earth, the surface just looks like that. It doesn't look like a curved surface like that. And these lines that come in are all pointing towards the surface of the Earth. And it looks like they're all just pointing straight down, and that it looks like they're parallel, right? This distance between lines stays the same. So it looks like the field remains constant, but if you zoom out, what really does happen is they get farther apart. All right? So is G really constant even in this room? No. It gets weaker and weaker and weaker the higher you get above the floor. All right? But how much weaker? Mass of the Earth, distance from the Earth's center squared, right? Well, the radius of the Earth is 6.6 million meters. All right? If you add 10 more meters to 6 million, but also square both those numbers and compare the results, the adding of 10 to 6 million, especially when you square it, has such an insignificant effect that we don't even bother talking about how much smaller G gets as you go up, until we start to talk about things not near the surface of the Earth, but out here where like a satellite would orbit, or where the moon would orbit, or stuff like that, where we can macroscopically say, yeah, the field really is weaker out there. Okay? Okay, let me back up. So, yeah, okay there? Okay. So, that was a little sidebar. So we can now, we've spent a lot of time talking about freefall, and we talked about freefall as being, the definition was, well, gravity is the only force acting on an object, and we said, that meant that acceleration is G, is 9.8. Well, acceleration is G, yeah, but that's not always 9.8, as we've hopefully seen. All right, if we go here, well, if this is the Earth, then G here is 9.8. But G out here, twice the Earth's radius away is 9.8 over 4, or 2.4 and change, 2.45. Or 2.45. Okay? But it's still g. It's just that g isn't really constant. So if we look at some place out here, a distance r from the center of this planet, whoops, it's not, distance r from the center, what's the gravitational field strength there? Well, the only thing we can say is g m planet over how far away we are. I'm going to call this planet and call this satellite. Satellite's not necessarily Sputnik, right, or one of those things. It's anything that orbits anything else. The moon's a satellite. All right? The object's linear acceleration, because if this is a, what we're sort of calling a free fall case, mass m is just, this is m, right? We'll call this m. How about we do this and call it mass satellite? We release this thing from rest. Well, how fast does it accelerate? Well, here's how fast, at g. And this is the field strength, but it's also the acceleration. And how do we know that? Because, well, we could do this and say this is fg. Right? And we could say, well, fg equals ma. Right? Mass of the satellite, that's the thing that would accelerate. So the acceleration is that, and right, that's how we got back to this. All right? Now, the object's weight, well, that's just gravitational force, right? So we can do that in a couple of ways. One is, well, m satellite g, or g m planet m satellite over r squared. Gravitational force is weight. Its weight changes depending on how far away the two objects are. All right, these are way harder to do kinematics problems with. You can't do this. You can't do like, well, okay, it's released from rest, and how fast will it be going after, going a certain distance? Well, the problem is A isn't constant, so it doesn't work that way, right? A varies with the square of, A keeps getting bigger and bigger because G keeps getting bigger and bigger. So you can't really do kinematics problems like this. You need to do calculus stuff. But they're certainly solvable, just not with our math. Okay? All right. Now, let's look at a different case where we talk about, forget having this object just released from rest. Probably. Let's say that this object is moving in a circular orbit at a speed v. That's not a force. It doesn't matter what direction it's moving, actually, so we'll just forget about that. But it's cruising around this orbit like that at a nice constant speed, but changing direction at a constant rate, right? And it's at an orbital radius that we'll call r. Well, the gravitational field strength there is still gm planet. What's up, Nuggy? Excuse me. The gravitational field strength here at this location we can write as g mass of the planet over distance from the planet center squared. Now, what we haven't said explicitly is why are objects able to move in circular orbits? Well, they do that because their weight, this object's weight, that is a gravitational force, points towards the center of its circular path. All right? So we've seen, the case where here's an object on a circular loop, and maybe it just lost contact, and mg points towards the center there, and yep, there's a place where it happens to point towards the center, and that's a time when gravitational forces can act, or force can act as centripetal force. But in this case, it's everywhere. Here's planet, here's satellite. Everywhere on this satellite's circular orbit, mg points in. Mg acts as the centripetal force. Okay, so we can say, well, weight. A couple ways to do this. One, well, that's m satellite, right? We're calling this m satellite. M satellite g. Well, remember what's g from up here? That's m satellite times g m planet over r squared. Oh, look, g m m over r squared. Sure, gravitational force. Right? Now, centripetal acceleration, we can do that in a number of ways. One of them is this. Okay? Well, the centripetal force is Fg, and that's, well, I can write it like this, over the mass. And the mass of what? The mass of the thing moving in a circle, that's the satellite, equals AC. Well, what's Fg over m? Well, remember, that's just g, right? Because here's Fg. Divide the mass of the satellite out, and what we get is that. All right, so we do keep saying, whether or not you know it, whether or not you recognize that that acceleration and field strength are the same thing. Now, do I mean like if we have, tension and friction and weight and normal and acceleration this way? No, that's not what I'm talking about. I'm talking about for a case where we're talking about a field force, not the contact forces like normal force and friction force and applied force and tension force. For field forces, the strength of the field, for gravitational field forces, the strength of the field and the acceleration that an object is given are the same thing. All right, speed, this is a neat one, right? We can do the same thing. If we say net Fc is mac, we can say that Fg is mv squared over r. Well, what m? Remember, the thing that's moving in a circle, satellite. And what's Fg? Well, that's a g, mass of the planet, mass of the satellite over r squared. Well, that equals m satellite v squared over r, and then we can say, oh, doesn't matter what's there. Look at this. Look at the expression we have here. You know what this is? Gravitational field strength. You know what this is? Centripetal acceleration. They're the same thing. We can even get rid of now a factor of r, so those are now no longer accelerations and field strengths. But we can write an expression for the orbital speed of some object at a given orbital radius. Now, I know I just said the orbital speed of some object, but I wrote mass of the planet. That's true, because how fast something orbits depends on some characteristics of the thing that it's orbiting around. Because ultimately it depends on the strength of the field that that object creates. Yeah, I understand if there's smoke coming out of your ears and blood coming out of your eyeballs. We're getting into a lot of different applications. We're getting into a lot of different ways to slice and dice a couple of formulas, and I understand that is challenging. All right. Let's look for let's look at a concrete example. Here's the moon. There's the Earth. Moon's average orbital radius is about that. Let's find its linear speed relative to the center of the Earth. And then its orbital period. And then the Earth's gravitational field strength at this distance from the Earth's center. All right, so let's do this first. Here's the moon moving in that circular orbit. We can draw a free body diagram for the moon. Done. We can write a net force statement for the moon moving in a circle. Not really a circle, but let's call it a circle. Fg equals m AC. Which mass? The thing that's moving in a circle. Whoops, I shouldn't write AC. I should write V squared over R. Well, gravitational force, G mass of the moon, mass of the Earth, over separation squared equals mass of the moon, V squared over R. Moon's mass is irrelevant. Get rid of a factor of R. Well, we just said this one, right? Mass of the Earth over R. And solve. You solve. B, the orbital period. Well, let's see. Oh, yeah, we got a V. And we want a T. A little bit for you to do. Okay, have I been clear enough about this yet? The reason, well, if you think back a couple of videos, the reason that we started talking about gravitational force, the whole reason we started talking about it was so we could talk about another example of circular motion. And that other example of circular motion is orbital motion. Disclaimer, yes, orbits are not circles, they're ellipses. But we don't have the mathematical power to handle ellipses in this course. So we'll assume that they're circular because they're pretty close. And for our purposes, it works just fine to talk about them that way. So the whole reason we started getting into all this was to talk about the physics of another kind of circular motion. All right. Along the way, we got into some pretty heavy-duty stuff like this, like gravitational field. All right, and the strength of gravitational fields and how they vary with the parameters of where those fields exist, right? And then how we can slice and dice, or here how we can draw some analogies between linear motion of an object in free fall and orbital motion of an object in free fall. Guess what? Things in orbit are in free fall, right? That's our definition of free fall. Gravity is the only force. Just because it's moving in a circle doesn't mean gravity's not the only force. Gravity is the only force. Things in orbit are in constant free fall. Okay? So we draw an analogy between one kind of free fall and another one. Again, I agree. Hard to keep all this stuff straight. I'll do my best, believe me, to give you lots of practice. Okay? So lots of good stuff, folks. I hope a couple things for you to do here at the end. You know what C is? Here's C. Do that. Find me an answer. Oh, yeah. Now, when you do this, when you find the orbital period of the moon, you're going to get a big number. But that number is going to be in seconds. Tell me if you know that. Tell me how you know that answer is right or wrong. Because you might know what the orbital period of the moon is, roughly. How long it takes the moon to go around the Earth. So do a little extra here. to confirm that you've done it right. Okay? Okay. Goodbye.